interrupt me if you have questions. So one-to-one functions and inverse functions. In 6.1, we did compositions of functions using f and g, right? When we composed f of g and g of x for that last example, it's forever ago, they turned out to be inverse functions because they simplified to x. Everything that happened in g, the reverse happened in f, or the inverse happened in f, right? It was divided by 5, and the other one it was multiplied by 5. They added 2 in one of them, they subtracted 2 in the other. The rule of inverse functions means that the two functions will undo each other and you will be left with x at the end, okay? Before we move on to inverse functions, we're going to talk about one-to-one functions. A function is one-to-one if all inputs if all inputs are unique and all outputs are unique. Okay. So for these three examples, we want to decide, is it a one-to-one function? If it is a one-to-one function, for every single ordered pair, x1, y1, x2, y2, x3, y3, x1, y1, x2, y1, x3, y3, x1, y1, x1, y2, x3, y3, for every single ordered pair in the one-to-one mapping, x is unique and y is unique, they will never repeat. Okay, unless they repeat with themselves, like you just make an actual copy. Okay, 1 second. Had to sneeze. X sub 1 is different from x sub 2 and from x sub 3. Each of those is a different value. Okay. For this one, sorry. Yeah, A. We'll call this A. We'll call this B. We'll call this C. Okay, for A, we have x sub 1, x sub 2, and x sub 3. There's no second arrow coming off of any of those. So no x value is used more than once. No y value is used more than once. y1, y sub 2, y sub 3, right? All x and y values are unique. The domains are unique. The ranges are unique. There is no repeating. So we would say this is a one-to-one function. That's the only rule for one-to-one function. All inputs are unique, all outputs are unique. Okay. Next, for B, we have x1, x2, x3. So our domain is unique. Each x value is different. No x value repeats, right? But the range is not unique. Y1 is paired with x1 and x2. That means x sub 1 is paired with y sub 1 if we're making an ordered pair, and x sub 2 is paired with y sub 1. Okay, y sub 1 was used more than once. It is not a one-to-one function. This is still a function, but it is not a one-to-one function. Okay. For the third one, for C, we have x sub 1 mapping to y sub 1 and x sub 1 mapping to y sub 2. So our domain is not unique. X sub 1 is mapped to, or is paired with, y sub 1 and y sub 2, right? These are unique. My range is unique. But my domain is not unique. If your domain is not unique, it is not a function. The rule for functions is that all x values must be unique. They're not repeated with a different y. To be a function, every x value has to be paired with one y value. As always, interrupt me if you have questions. Tell me whether this function is one-to-one, okay? So we have our input, we have our output, or our domain, and our range. Right? Let's go through the mapping, because the mapping is separate from the ordered pairs. Okay, so for the mapping, let's go through the list of the domain. 35, 41, 45, 53, and 62. This is unique. No x value is repeating. Over here, we have 59, 55, 35, 33. However, look at how the arrows are moving. So this has one arrow coming out, one arrow coming out, one arrow coming out, one arrow coming out, one arrow coming out. However, one arrow, this has two arrows. 35 is not unique. (41) and 53. 35 is paired with 41 and 53. So we would say not unique. If your y values are not unique, it is not a 1-1 function. So you write it 1:1 for this mapping. The mapping is not a 1-to-1 function because the 35 is paired with the 41 and paired with the 53. Good. All right, down here we have ordered pairs, completely separate. Okay, different thing. We have our domain as our x values. Then we have our range as our y values. Okay, the x values, are they unique? -35, -3, -2, -1, 0, and 2. They are unique. My y values are 5, 3, 1, -1, and -3. I think that is unique. If you do not have any x's or y's repeating, it is a 1-to-1 function. Hold on 1 second. Yes. Sorry, I missed that, but yes. It is not a 1-to-1 function. It is still a function because each x, sorry, I went back up here. This is not a 1-to-1 function, but this is a function because each x maps to its own number. X is not repeating, so it's still a function. For this first one. Okay, now we're moving on to the second one. X values are unique and y values are unique, so we can call this a 1-to-1 function, which means it obviously is also a function. Yes, tell her she is welcome to watch the video later. Not a problem. Thank you for letting me know. All right. So that is when you have a list of ordered pairs or a mapping, anything with a domain and a range in a list form. But if you already have a graph, we can take a test with a graph. If you remember the vertical line test, the vertical line tells us whether it's n function, tells whether it is or is not a function. If it passes the vertical line test, it is a function, okay? For determining if it is a one-to-one function, you can take a horizontal line test, because remember, the rule for one-to-one is all x's are unique and all y's are unique. When you look at this graph in example 2, okay, you see a parabola, it would pass the vertical line test. A parabola is a function. If you took the horizontal line test, you made a horizontal line through the parabola, it would not pass the horizontal line test, right? It fails the horizontal line test. So this fails to be a one-to-one function. Okay. The inputs are unique. The x values are all unique. It will pass the vertical line test. It will not pass the horizontal line test. The outputs are the same here, right? We have different x's, which is my domain or my x, and then my range or my y is repeating. My range is not unique. Good. Here, this is interesting because they didn't give us what the actual graph is, but I'm going to pretend that it's the graph of y equals x to the third, right? Because we know that that is just a big slithery s, right? I can't see it. I don't know without more information whether it would pass the horizontal line test. It looks like it'll pass the vertical line test, right? I don't know if it'll pass the horizontal line test, but if it is truly y equals x to the third, it will pass the horizontal line test. No matter how far you zoom in, even though it looks like it's a straight line here, it is, each point is unique. It is slowly moving up as you move to the right. Good. So y equals x to the third is a one-to-one function. So I assume this is a one-to-one. Horizontal line test works just like the vertical line. So those were one-to-one functions. Basically, what you need to know is x's are unique and y's are unique. If x's are unique, it's a function. If x's and y's are unique, it's a one-to-one function. Okay. Inverse functions. If y equals f of x is a one-to-one function, then f has an inverse function. Okay, let's talk about the end, since it was so very long ago. Let's talk about the end of our previous lesson. Okay, what we had for the end of that lesson was f of x is 2x minus 5, and we had g of x is x plus 5 over 2, right? When we put in g of x for x, so when we took the composition of f of g of x, which can also be called f of g of x, the answer was x, right? When we took g of f of x, and we solved it and simplified it down, we got x. If you analyze the functions 2x minus 5 and x plus 5 over 2, the rules undo each other. Multiplication by 2 is undone by division by 2. Subtracting 5 is undone by adding 5. This is the test you use to determine if two functions are inverse. F of x and g of x are inverse functions. We're doing the inverse of subtracting 5. We're doing the inverse of multiplying by 2. Good. So if y equals f of x is a one-to-one function, f has an inverse function. So every one-to-one function has an inverse function that is a separate function undoing f of x. The symbol f (-1) is used to denote the inverse function of f and is found by switching domain and range. Right? Domain is x, range is y. We're saying switch x and y to find your inverse function. All right. If you have f of x, f (-1) of x will be what happens when you take y and replace it with x, take x, replace it with y. Okay. The graph of a one-to-one function f and the graph of its inverse function, the inverse of f of x, are symmetric with respect to the line y equals x. Okay, and so remember, if you think about the line y equals x, that just means when y is 0, x is 0. When y is 1, x is 1. When y is 2, x is 2. When y is (-1, x is (-1), right? So it's just this line straight through the middle of quadrant 1 and quadrant 3. Good? Okay, so if we look at this graph, we see y equals f of x and y equals the inverse of f of x. So if this is AB, this is going to be BA. Okay, let's make up some numbers. AB looks like it could be 1, 2, right? 1 on the x, 2 on the y. That means right here we're switching them. So this becomes 2, 1. We switched x and y. It's inverse. It's the inverse function. It's the same distance to the line x equals y. So that's the same as that. That's the same as that. That's the same as that. Good. If this one is (-1, 1, this one becomes, or this one will be 1, (-1) because it's the inverse. Good. Okay. So now that we know how the inverse works, that you just switch x and y, I can go back to f of x equals 2x minus 5 and say that g of x is f of x's inverse because when I composed g of x with f of x, they cancel one another and they leave only f of x equals x, which is, right? G of x equals x is the same as y equals x, which is the same as that line. So when you compose two inverse functions, they move to x. They cancel each other out and they just move to y, the line y equals x. Good. So g of x equals x, f of x equals x is the same as y equals x. So it's all coming into that line. The line y equals x is just whatever x is, y. Look at example 3. The graph of the figure shows a one-to-one function y equals f of x. Draw the graph of its inverse. Okay. They have for us some function. They have named this function f of x. Okay. We know what the equation looks like. We know what the function looks like. We know it is a function because it passes the vertical line test. And we know it is a one-to-one function because it passes the horizontal line test. There are no arrows, so it doesn't go on forever. It will pass the horizontal line test. It will pass the vertical line test. So it is a one-to-one function. Oh, and they already told us it's a one-to-one function. If it's a one-to-one function, it has an inverse. So f inverse of f of s exists. How do you find this? You switch x and y. Okay. So they want us to draw the graph of its inverse. Find the inverse of f of x by switching the x and y coordinates. Switching x and y. Okay, that's what I want you to take away from inverse function. F of x becomes its inverse when x and y are switched. And then we can simplify it to a y equals, right? So we switch x and y and we solve for x and y if it's an equation. If you already have points, you just switch the points x and y. Let's talk about what we think each of these points is, okay? Here we have our first one on the right is 2, 2. Agree? Okay. Here we have our second point is 1, 0. Here we have -2, -1. Yeah. So to find f of -1, f -1 of x, find the inverse, I switch x and y. If this is -2, -1, oh, let's write it down. So f of x has the points 2, 2, 1, 0, and -2, -1. The inverse has, we're going to switch x and y. In this case, it's not super exciting. It's just still 2, 2. Going to switch x and y, it's 1, 0. It becomes 0, 1. Switch x and y, -2, -1 becomes -1, -2. Good. That is the inverse of that. Now we can graph this. 2, 2, same spot. 0, 1 is right here. -1, -2 is right here. There's a little fish. And we want to remember that it should be equidistant. All those points should be equidistant from the line y equals x. And it looks like it is. Good. Draw the graph of its inverse. We drew the graph of its inverse. If it goes down, if it starts at 2, 2 and goes down, this one starts at 2, 2 and goes left. Cross right there. All right, what if you needed to find 5, 6, yeah. What if you needed to find the inverse of a function algebraically? You don't have the graph to just switch the points, right? You are just going to replace f of x with y, switch the variables x and y. So wherever x was, it becomes y, wherever y was, it becomes x, and then solve for y. Okay, don't skip that step. So we're switching x and y, but we still want it to be an f of x function, so we need to solve for y. And then we take that y and replace it with the inverse of f of x. Good. For example, if you had y equals x to the 5th, and you wanted to find the inverse of y equals x to the 5th, what you're going to do is you're going to switch x and y. So we say x is y to the 5th, right? And then we just solve for y. I don't want it to be the 5th power of y. So I'm going to take the 5th root of y to the 5th and the 5th root of x. And we're going to say y is the 5th root of x. Good. What undoes raising something to the 5th power? Taking the 5th root of it. What undoes taking the 5th root of a number? Raising it to the 5th power. But we need to prove it. So we take the composition of the two functions, and if you are left with only the variable, that proves mathematically they are inverses of one another. Okay. Verify that g of x equals x to the 5th, and the inverse of g of x equals the 5th root of x. Okay, so we know that if we switched these and solved for y, we would get the fifth root of x. But now we need to prove it, and we're going to prove it by doing the same thing we did on Friday, which is take the composition of g of x and the inverse of g of x. So if g of x is x to the fifth, the inverse of g of x is the fifth root of x raised to the fifth, right? I put in the inverse for x, left everything else the same, right? I replaced x with the fifth root of x, but I left that the same. Now we're just going to solve, okay? So I'm going to write it again. G of g, the g of the g of inverse of x is the fifth root of x to the fifth. We know that the fifth root of taking fifth root of something that is raised to the fifth power cancels, and we just get x. So we have proved mathematically that these two are inverses of each other. Good. Now I have f of x equals 4x minus 7, and the inverse of f of x is 1/4 x plus 7. Good. F of the inverse of f of x is 4 times, instead of that x, I'm putting in all of this, okay? 4 times 1/4 times x plus 7 minus 7. So all of that where the x was. Good. Now I'm going to multiply. I'm going to just do algebra now. So I have 4 times 1/4 x plus 7 minus 7, because the 4 does not carry to the negative 7. All right. 4 times the 1/4. I could distribute the 1/4 and then distribute the 4, but I know that 4 times 1/4 just becomes 1. So that is now 1 times x plus 7 minus 7. I don't need to multiply it by 1. I don't need to distribute the 1 because it's just 1. So it's x plus 7 minus 7 equals x. Okay. So I just proved that those are inverses of one another algebraically by putting in. And you can put it in whatever order, right? You could say the inverse of the inverse of g of x is fifth root, and instead of that x, I'm going to put in x to the fifth. You still have the exact same thing. Okay, it doesn't really matter what order. Here it would have been the inverse of f of x is 1/4 times 4x minus 7 plus 7. You can still see how minus 7 plus 7. Right? You can still see how those cancel, and you have 1/4 times 4x. Those cancel just like they did up here, and you have x. Doesn't matter which order you put it in. All right. Okay. Last tiny bit. Find the inverse of f of x equals 3x minus 5. Graph f of x and the inverse of f of x on the same coordinate axis. Okay, so we need a coordinate axis. 3x minus 5, right? I'm just gonna make an XY table for 3x minus 5. So that's f of x. When x is 0, right? 3 times 0 minus 5 is -5. So that's the point. 0, -5. When x is -1, we'll say 3 times -1 minus 5 is -8. That's the point, -1, -8. When x is a +1, we're going to get 3 times 1 minus 5, which is -2. That's 1, -2. Right? So there are my points for f of x. Zero, -5. -1, -8. +1, -2. And continuing, right? 2 would be 1. So that's 0, -5, -1, -8, 1, -2, and 2, 1, right? So that's the graph of f of x. F of x equals 3x minus 5, right? And we can now take it algebraically, right? X is being multiplied by 3, x is 5 is being subtracted from x. So if I want to find the inverse, I need to think about what undoes multiplied by 3 and what undoes being subtracted 5, right? But algebraically, I can just say that becomes y equals 3x minus 5. So first I substituted y in for the f of x. Then I'm going to switch them. Okay, so now I'm going to say x is 3y minus 5. Now I'm going to solve. Right? X equals 3y minus 5. Solve for y. Add 5. Add 5. So we have x plus 5 equals 3y. Divide by 3. And I am left with x plus 5 over 3 is y. Good. So f of x is 3x minus 5. F -1 of x is x plus 5 over 3. Okay, I'm going to make a table just like I did here of the inverse and see if it's true. Okay, so I have my x values, I have my y, and I have the point it will make. Here I have 0, -5, -1, -8, 1, -2, and 2, 1. So I think I'm going to start with x as -2 so that I can confirm or deny this one and this one. Okay, so I'm going to do x is -2 and x is 1 because I'm switching my x and my y. So when x is -2, that means I'm taking -2 plus 5 and dividing it by 3. -2 plus 5 is 3. 3 divided by 3 is 1. So my point is -2, 1. When it's 1, I have 1 plus 5 over 3 is 2 because 6 divided by 3 is 2. So I can say that the graph of the inverse of 3x minus 5 will have the points -2, 1, and 1, 2. -2, 1, 1, negative. This should be -2. 1 plus 5. No, it's okay. 1, 2. All right, I just don't like how it looks. I'll do when x is -2. I'll do it when x is -5. -5 plus 5 over 3 is 0. So when I get all the way to 2, 3, 4, 5, here I should be at 0. I guess I just don't like the way I draw the coordinate plane. All right, we see that we have the inverse, right? If I move it up. 0, -5 becomes -5, 0. 1, 2, 1 becomes 1, 2. 1, -2 becomes -2, 1. And if we look at the line, y equals x, they are parallel on that line. So you can find a bunch of points and just do the opposite, graph it, or you can take it algebraically, change y and x, and solve for x.